Yeah, so anyone who doesn't know me already, I'm the weird guy who asked the bird net question. And yeah, I spent March and April on a drill ship, basically drilling off the coast of New Zealand for 2 months, doing 12 hours on, 12 hours off, and it was pretty intense. And I'd like to tell you about the sort of things we kind of figured out, or are trying to figure out anyway. So just a general overview of the talk. I'm just going to go around the basics, kind of a 101 primer of ocean drilling, and then into the actual objectives of the cruise, and then the kind of biostratigraphy we used and kind of initial findings as well. So there's going to be loads of pictures of sunsets as well, because they were really pretty. All right, so basically, kind of deep sea exploration drilling started with the Challenger expedition in the late 1800s, which was basically just dredging certain parts of the ocean. It was basically the advent of paleoceanography. But it really came into its own in the late 50s and early 60s with Project Mohole, where basically they tried to drill into the Moho, which is very, very far down, and they got about 100 meters, but it started out, it was proof of concept that we can drill into the ocean crust while in the water. So then, the deep sea drilling project then started, which is an international collaborative effort which has been going since 1968 and has taken on a number of forms, moving from the DSDP to the ODP and then the IODP twice. They had to change from drilling to discovery because after Deepwater Horizon, you don't get any funding if you have the word drilling in a scientific venture. So the general objectives of the IODP as a whole is basically what you'd expect. Anything we can figure out from drilling the ocean crust if it comes to climate, deep time, life, and geohazards, geohazard was the primary objective during this cruise. So the general operations, there are three kind of platforms we use to drill. There's the JOIDES Resolution, which is a riserless vessel. Basically, you don't get any circulation back to the ship. That's what a riser does. Then there is the riser vessel CHICU, which is about twice the size of the JOIDES, and it's about 200 meters long, something like that, which can drill a lot deeper. And then we have mission-specific platforms, such as drilling the Arctic. You need Russian icebreakers to break up the pack ice, and then heavily fortified kind of drilling vessels, and also jack-up platforms like the one that was used to drill the Chicxulub crater a couple of years ago, which I'm sure we're all familiar with. Oh, excuse me. So we actually used the JOIDES for this one, which is the one which has been used most since the 80s. And it's basically this derrick in the middle, and a drill pipe hangs down through what's known as the moon pool, which is it's very pretty. You're not allowed to go into it, and you're definitely not allowed to push anyone into it, because it's not the moon door. So how are we drilling? Basically, this drill pipe is hanging off the ship down to the seafloor, and it's not conventional drilling. It's not like you're drilling into like a piece of wood with a screwdriver. You're actually pulling the string up because it's about 230 tons hanging off the ship. So if you let go, then it would just kind of fall down and possibly break the ship as well, which would be kind of bad. So because it's up to like 5,000–6,000 meters of tensile steel, it's actually more like trying to drill with a spaghetti string. I didn't make that, so I know it's weird, but yeah, you get the concept. So these are the kind of things that we use for drilling. So the first one is the advanced piston core, which is basically we advance 10 meters at a time, and this top bit up here is like a cutting shoe. So basically we build up pressure behind it. There's two shear pins which break, and it fires a piston 10 meters into the sediment, and then we draw that back up. The second one, I've got a prop as well. It's in XCB, which is an extended core barrel. If anyone wants to have a look, pass it around. It's very heavy. Don't drop it, it won't break, but it will break you. Which is, yeah, so once we're getting harder sediments, which we can't just core into it like clays and stuff, we start to use this for marls and more calcareous consolidated sediments. And then once that stops working, because these things break after a while, we had one which was worn down by about a foot because it just got so hot. We move on to rotary coring, which is just big tungsten carbide teeth which just kind of break everything apart. So the reason why we do these different methods is because when we have just a piston, we get nice preservation of like stratigraphy and like paleomagnetism and fossils, whereas if we have rotary coring, it kind of chews up the sediment a bit too much. So the expedition objectives for this one was looking at the subduction zone between the Pacific plate on the right and the Australian plate on the left, because we have a lot of earthquake activity here, and well, it's a site of what's known as slow slip events, which are basically earthquakes which can last for several weeks, but it may sound like, oh, they're not as bad as like instantaneous earthquakes, but still we get damage like the recent Christchurch earthquake, which killed around 200 people and basically broke the infrastructure of the country. So in this specific cruise, this is a cross-section of the subduction margin. So here's the Pacific plate being subducted underneath the Australian plate here. Here's the margin of it. And we drilled 4 holes to kind of look at the kind of general character of earthquakes and sediments which are going in. But I'm going to concentrate on these 2 because these were the most interesting biostratigraphically. There's a big bird. Bio, you know. So the first site is a HSM 05 or 1520, which is what it was named on the ship. Where basically the objective was to just look at the age, determine it from forams and nanofossils. So here we have the actual lithology. So as you can see, it's mainly this top 500 meters or so is mainly just siliciclastic, a lot of turbidites. It was pretty much about 3 meters per 1,000 year sedimentation rate, very, very fast. So it wasn't very interesting biostratigraphically, but then we move into more calcareous sediments, and suddenly this is a stick-on. The age rapidly goes up from, as you can see here, Neogene up into the Cretaceous. We're getting about Cenomanian-Turonian boundary stuff. These are the kind of lithologies we kind of encountered as we went down. Like they changed significantly from marls becoming more carbonate-rich to chalk. And it was scattered with debris flows and chunks of basalt lying in there, which was a pain in the ass when you're trying to figure out the age of a rock and there's stuff already ripped up into it. And then here's an interesting kind of invertebrate thing. We've got a escape structure where we had a debris flow come in and some things tried to get out, moving a good like 20 centimeters upwards through the sediment. Closer look. And then, so as we went down further, we got to about 830 meters, and then suddenly it looked like we were about to hit the KPG boundary, and then bang, volcanoclastics came in, which are horrible. There's no fossils preserved at all, which is really annoying because I wanted to see the boundary layer. Obviously, we all do. So then we had several hundred meters of this with small, different beds kind of interbedded between them. So the one that I was really interested in was this dark one, which was named San because it was Japanese at first because we drilled it really weirdly. Where I thought it was just kind of basalt or something at first, but then the geochemistry team found a 4% total organic carbon content within one of these layers, which was really interesting because that would infer anoxic conditions, and it turned out to be a marl. So looked into another wedge where it was 15%, and the only times you really get that is in proper ocean anoxia events, and because we knew within the Cretaceous it could only be certain ones. Interbedded with it were these white layers, which happen to be radiolarian-rich sands, which is indicative of the Bonarelli section in Italy, which is OAE2, the Cenomanian-Turonian boundary section. So there's a very good chance we have a new high-latitude record of the OAE2, which could be quite useful for global paleoceanographic reconstruction at the time. So the other site was 1526 over here, which was drilling into this seamount. So it was about 100 meters, and it was just to determine the age again, and was it ever subaerially exposed, which is quite important for the tectonic history of the region. So we had a top cover of about 20 to 30 meters of generally pelagic sediments. This is a cross-section through it. You can see it's rapidly changing, and these layers are unconformities. So we switch from Pleistocene to Miocene to late Cretaceous, actually, which is some of the best Cretaceous I've ever seen preserved because it's been above the CCD for like 70 million years. And we also have more invertebrate stuff, so we had a lot of shelly layers, which was really interesting because I was the only macro paleontologist, well, I'm a micropaleontologist, but I've done macro on board, so they asked me to take a look at it. I took a couple of fin sections in there, and I was like, what am I going to be able to tell about this? It happened that there were these structures in here, which I talked to a couple of people that I know and confirmed that they're actually rhodophyte algae. So that gave us proof that at some point prior to that sedimentation occurring, we were actually in the photic zone. So this specific genus was about 150 meters water depth maximum. So really useful, really good to, it'll be a really fun kind of project to kind of deviate away from forams, which is what I normally look at. So that'd be a cool little collaborative work with people on the boat. So the next step is to start writing all of this sort of stuff up. So that section where we had really high sedimentation rates, we're going to get centennial scale geochemistry records of the last glacial interglacial cycle for the last 120,000 years or so, and see if we can get like really good records from that. And then just working out the general biostratigraphy and taxonomy of the Cretaceous, especially, which is a really good high latitude record. And then Have I written that twice? I have, yeah. No. Yeah, and then this will be a collaborative paper with geochemists and sedimentologists recording the OAE and what context that has for a high latitude site. And then, of course, just the entire section just going through the biostratigraphy, integrating with nanopaleontologists, radiolarian and palaeontology, and also paleomagnetists and volcanologists, because there's a lot of ash in there which we can date geochemically. So it's like a six-fold kind of chronology for like the Southwest Pacific, which has never been done before. So I'd just like to thank all of these things around here. There's a lot of them, and also thank the Palace for giving me a travel grant to come here and present this work, and the entire expedition party, as well as my supervisors down here. And that's the science party, and that's the entire expedition. About 120 people on board, and couldn't have done it without any of them. And here's a squid bumping into a drill pipe. Cheers.